In this lecture, we'll be taking a closer look at the development of storms as they relate to the troposphere. The Earth's atmosphere is an extraordinarily dynamic medium. As your author points out, if the Earth were a non-rotating sphere with a uniform surface, we could expect a very simple system of circulation, both in wind and in water. But as we know, the Earth does not rotate. And in addition to this, it has an extremely varied surface. As a result, we have a very dynamic and nearly unpredictable system of circulation that results in the development of many of our storm bodies. This image is an idealized global circulatory system. It also provides us with, I would say, all of the natural actors that contribute to the development of storms. Right away, you will notice that we are dealing with two very important phenomena that will, in a sense, geographically localize themselves very close to the equator. We will recognize these Hadley cells, which I'll describe in just a moment, to the north and the south of the equator. These tropical systems of circulation and air currents are, in a sense, named after George Hadley, born in 1685, an English meteorologist who first conceived the idea of enormous convection air currents that will, in a sense, be localized to our tropical environments. It is the interaction between the warm air associated with these lower latitudes and the warm waters that we associate generally with, again, the tropical and subtropical environments hugging our global equator. The interaction of these will develop these convection air currents. Another contributing factor will be when warm air is rising up into the lower troposphere, we have a cooling effect, bringing it back down close to the surface, creating these kind of convection currents. These convection currents are extremely important not only for preserving life on the planet and circulating the chemistry of our atmosphere, but also, as I said before, they're very important for our understanding of how storms work. Along with these tropical circulatory systems, we recognize, in a sense, 7 additional forms of air current or wind action that will contribute to much of our weather and its predictability. We recognize trade winds, which I'll define in just a moment, subtropical highs, polar easterlies and polar highs, the development of polar fronts, westerlies, and what is referred to as an intertropical convergence zone. All 8 of these basic patterns are important to understanding tropospheric circulation. We have already discussed the Hadley cells. I'd like to now go over the additional 7 concepts that you see depicted in this image, and I'll give you just a surface understanding of each of those 7 components to this tropospheric circulatory pattern. Your readings will expand on this greatly. I'll start with the subtropical highs. When we look at our oceans, we realize that these ocean bodies are semi-permanent high-pressure cell environments. Subtropical highs, which are the label that we give to this phenomenon associated with the lower atmosphere, are centered at approximately 30 degrees latitude, both in the northern and southern hemispheres. These anticyclonic phenomena associated with the mid-latitudes of both the northern and southern hemispheres are very important for our ability to predict weather patterns for the summer and winter months across many of our major land masses, again in the northern and southern hemispheres. Another major wind system that we associate with warmer climates, specifically in this case the tropics, are the trade winds. These winds cover a huge portion of the Earth's surface and are localized to latitudes, again, 25 degrees north and 25 degrees south. These trade winds are going to move air particles, and again, they're going to affect current patterns as well associated with surface flows of our ocean bodies, generally moving particles from the east to the west. Meteorologists and climatologists consider the trade winds to be the most reliable of all of these circulatory components. The predictability and size of these wind patterns made them an important part of the age of discovery. The northern and southern trade winds will converge. They'll converge along the equator, and they will be an important part of another component in this circulatory system, the intertropical convergence zone. It's usually abbreviated capital ITCZ. Often referred to as the doldrums, this is a geographic location, again spanning the entire planet, wrapping kind of the entire equatorial region of the planet, where northern and southern hemispheric winds will converge and mix with one another. If we move our eyes to the north and to the south of this equatorial region and move into polar regions, we recognize another important contributor to air disturbances within the tropospheric system of circulation. They will also be major actors in this circulatory system. High pressure cells are situated above our polar regions, both in the northern and southern hemispheres. These phenomena are referred to as polar highs. In this phenomenon, we see warmer air being moved generally down and horizontally across water and land masses in the northern and southern hemispheres. In the northern hemispheres, the circulatory patterns which result from this generally will be in a clockwise fashion, while they will be counterclockwise in the southern hemisphere. If we move below this and approach the 60th latitude, both in the northern and southern hemispheres, we recognize the presence of the polar easterlies. Winds in this case will move generally east to west, and we will see the air masses associated with, geographically, the location of these polar easterlies to be both cold and dry. In the northern and southern hemisphere, we also see the development of polar fronts. Generally, polar fronts will exist somewhere between 50 and 60 degrees latitude. This is a very dynamic region, geographically, with regard to how the circulatory system of the troposphere behaves. Why is this? Well, we see not only extremely cold winds of the polar easterlies, for example, converging on this location, again, of latitude. We also see the relatively warmer air associated with the westerlies also converging on this land or on this region. And when we have this convergence of extremes, both in cold and warm air, we start to get some very unique circulatory patterns. So too, we get air flows associated with surface temperatures of exposed water and land in this region. These air flows rather, will interact with one another and intensify this very unique, very chaotic kind of system of interaction between westerlies and easterlies, between the cold and the warm. So the polar front area is again a region wrapping around the planet that is characterized by the rising of air currents, stormy conditions, relative cloudy skies, and a good deal of precipitation, in this case predominantly in the form of snow or of some sort of semi-frozen precipitation. The final component that I'll share with you today, and again, please cross-reference all of this material with your readings, are the westerlies, which I would say are probably second to the Hadley cells, a very important contributor to the overall circulatory pattern. The westerlies, and again, I would say this is a very generic label for a lot of circulatory activities within the region. Generally, the westerlies will be localized in terms of latitude in the northern and southern hemisphere to an area between 30 and 60 degrees. The westerlies will contain areas which are a little more stable in terms of circulation, and then others that are in a very dynamic state of change. One of the areas within the westerly phenomenon that is in this more dynamic expression, and it's associated with quite a bit of high speed wind, are the jet streams. We recognize two main types of jet stream that are again closely associated with the movement of storms and of precipitation patterns across these mid-latitude environments, both in the northern and southern hemispheres. We recognize a polar front jet stream. Again, this would be the most north, and we recognize a subtropical jet stream at high latitudes, again in the westerly phenomenon. Ironically, we can consider these unique high-speed phenomena within the westerlies to be core areas with regard to how the westerlies contribute to tropospheric circulation. Rossby waves are also something to consider when we're talking about, in this case, how these jet streams behave, or how these dynamic core areas within the westerlies are behaving. Named after the Chicago meteorologist C.G. Rossby, these Rossby waves generally will be associated with our polar front jet stream. The Rossby waves themselves, and there's multiple waves that we associate with this phenomenon, will generally take these linear images on the graphic that you're looking at here, and they will create a more wavy pattern as we have colder air, drier air in the northern latitudes, or in the extreme southern latitudes, interacting with warmer, moisture air associated with tropical and subtropical, predominantly subtropical regions, both in the north and the south. The amplitude, or how these particular wave patterns develop, their size, and where they are situated on the geography of the planet, both in the northern and southern hemisphere, will be very important for our understanding of how weather patterns behave, how air masses will, at least on their edges or on the margins of air masses, how they will express varying weather patterns, and then also how we can track out major disturbances or disturbance phenomena within, in this case, the atmospheric circulation of the troposphere. Again, a circulatory pattern that's important to understanding how storms behave and ultimately how we can attempt to predict them. So as the jet streams bend to the north or to the south, whether these jet streams are associated with cold air or warm, moist air, we will get a sense of what to expect in our local environments. Will we have a warm day with the chance for rain? Or will we have a cooler day, maybe associated with the onset of autumn or winter? So again, understanding how these jet streams behave, how they fluctuate over time, and then how we can use them to predict how we experience the atmosphere on the surface of the planet becomes very, very important and becomes a real key to understanding weather. All right, let's take a look at some of these atmospheric concepts and directly tie them to storms. So as is the case with any future prediction, climatologists and physical geographers and geomorphologists have attempted to predict the future of our earthly air masses and how we will experience changes in those earthly air masses. Air mass analyses and strategies associated with how we analyze these varying expressions of air on the planet began with the work of two World War I meteorologists from, in this case, Norway, Wilhelm and Jakob Yerkes. Wilhelm and Jakob analyzed air masses and their changing conditions over time. They found this to be very useful in terms of predicting storm activities and generally weather patterns in terms of whether or not we would have a dry, warm weekend or a cooler, moist weekend, or how our seasons might be experienced from one year to the next. Well, let's look at some key terms. First, what is an air mass? Well, an air mass is something that extends over 20 to 30 degrees of latitude. It's going to be an air phenomenon, something associated with the lower troposphere and its system of circulation that will generally be sitting on the surface of the planet. And again, it will extend in terms of its overall geographic size, or geographical size rather, between 20 and 30 degrees of latitude. Another way to think about it is that it is a large body of air, sometimes subcontinental, that moves through the Earth's troposphere at a very predictable rate. Let me repeat that. So again, another way to think about it is that it's a large body of air, sometimes subtropical or subcontinental rather, that moves through the Earth's troposphere at a predictable rate. Now, understanding the center point of this geographically, of this air mass, becomes very, very important because we want to track its development and its movement as well. So what is a source region? A source region in this case is earthly space that is integral to determining if there is a shift in an air mass, or whether that air mass is stable or unstable in terms of its outcomes, the weather characteristics. In a sense, a source region is the place where the air mass originates. Please note that there are only a couple of places on the planet that will be producers of air masses. We'll talk about the source region that has the greatest impact on the seasonal weather patterns of the American Midwest, just because that's generally where our college is located. But there are a handful of source regions across the planet, both in the northern and southern hemisphere. For a source region to produce a long-term air mass, it must be homogeneous in its elevations, in its water resources, the kinds of plants and animal resources that exist within this region, and the atmospheric chemistry of the region. So again, just to reiterate here, source regions have to be fairly stable. They have to be homogeneous in terms of their overall roughness, in terms of the changes in elevation on the surface, water resources, the size of open water, for example, and water temperatures, plants and animals that will inhabit the ecosystems across the region itself, and then, of course, the atmospheric chemistry. We'll be taking a closer look at two source regions and the air masses that are associated with them. Please reflect on this map and compare it to what you have in your readings as you are kind of taking all of this in. We'll be looking in this lecture at the marine tropics and the continental Arctic. Now, let's back up for a minute and just kind of connect all these pieces, because I've been bringing a lot to the table in this lecture today. When you think about some of the key concepts, dwell on this. Air masses, like climates, are classified. Hundreds are recognized. However, we only recognize 5 due to their geographical size and ultimately their predictability. Generally, when a physical geographer or a geomorphologist is attempting to understand how the atmosphere is impacting landscapes on the planet, and of course the animals and plants that dwell within those landscapes, they recognize, again, these 5 major air mass types. They'll take a look at tropical air masses. They'll look at polar air masses. They'll look at Arctic air masses. They'll look at continental air masses. And they'll look at marine air masses. Well, then, how do we look at specific areas within these 5 major air mass types? Well, let's take that marine tropical air mass example with that marine tropical source region for a moment. A marine tropical air mass encompasses the tropical and subtropical oceans generally. It is a stable air mass. The only constant instability in its weather expressions is found along the western coastlines of its major ocean bodies. How is weather experienced in a marine tropical air mass? Well, first, we will generally see high average temperatures year-round. Second, we'll see high expressions of humidity. Third, in terms of cloud formations, we'll see a lot of cumulus clouds. We'll see convection storm activities. And finally, we will associate heavy precipitation in all 4 recognizable seasons within this marine tropical air mass phenomenon. Well, you may ask also, how does this concept of how we experience an air mass tie to the idea of an air mass's source region? Well, generally, think about the source region for the marine tropical air masses. And you can look at the map that I have here for you to get a sense of where that might be. Generally, we will see a marine tropical air mass associated with warm oceanic water. And its region, its source region, will be directly within that warm water environment. And of course, the air just above that warm water environment. Let's juxtapose that, again, the marine tropical air mass, with a continental Arctic air mass, which again has a source region that we associate as continental Arctic. A continental Arctic air mass, please look at the map that I have for you, encompasses places like the Arctic Ocean, Greenland, and Antarctica, at least on this image. It's considered to be a very stable air system with very cold air and very dry air. It will have four characteristics that we can associate with how life is experienced in this air mass environment. First of all, the continental Arctic air mass seldomly moves south. Second, generally we will recognize it to have clear skies. Third, sub-zero temperatures are very common. And fourth, relatively calm storm actions are associated with this very large continental cold air mass. Again, its source area would be a continent, and you can see where that is on this image. So everything that we've talked about up to this point is very much interconnected with each other and can very much be recognized within this image. We know that wind and air circulation associated with our troposphere is a major contributor to how we experience patterns of temperature and precipitation on the planet, and ultimately how we experience weather on a day-to-day or even annual cycle. Then the temperatures that we associate with air and water particles anywhere on the planet and geographically embedded within these air mass environments start to, in a sense, provide us with the factors that produce the characteristics of these air masses. So we will start to see the development of source regions based upon where we are on the planet and ultimately how much surface land or surface water is available and the temperature of that land and water environment. Once we see that, then we step back and we start to see the development of these air masses. And along the edges of those air masses, we start to have much less predictable phenomena in the sense of developing storm activities as one air mass is interacting with another, or one is moving onto another, or vice versa. This is how we experience weather. This is how we experience our storms. And ultimately, it takes all of these variables and ideas into consideration at the same time. The thing we have to remember is that an air mass, for all its stable components, for the stability of its source region, does change. These are all dynamic systems, and nothing is closed. One of the things that we have to keep in mind, or one of the things that we have to track in a sense, and this is what the Yerkes brothers were really closely looking at, is how an air mass will move over time. Time in terms of a shorter scale, an annual cycle, and time in a much larger climatic cycle, maybe one over centuries, if not millennia. When a common or historic movement occurs within an air mass, generally the air mass itself remains stable. However, we start to see the development on its margins, or geographically at the margins of these air masses, some unique kinds of interactions. Annually, tropical and Arctic air masses will converge in the center of the United States. They will then move toward the western coast of the United States and of North America and the Pacific Ocean. Right? So they'll come together and then they'll slide past one another. These air masses change as they move away from their source regions, and they do this on an annual cycle. They will take on moisture and become generally warm at periods of time. Other times they will let that moisture go and start to cool. This means that air masses moving throughout our hemisphere become increasingly dense. The physical quality of borders will remain. However, we will see the development of these very dynamic fronts, cold fronts and warm fronts. and we will see the patterns of these fronts and how they develop change along the margins of these interacting air masses. And we'll see this occurring over time. When these fronts develop and when we have air masses, at least the borders of air masses, interact with one another, we start to see the development of unstable areas. Very pocketed, very small, but unstable. And this is what leads to the development of storms. Some examples for you. The marine air mass over what is today the Gulf of Mexico. Well, it's a tropical air mass, and it generally will move on shore during the summer months. The land is warmer than the air moving onto it. What happens? Convection air currents arise, and the moisture in the air condenses as rain. Pretty heavy rain. When an air mass is commonly cold, such as a continental air mass, it is much more stable when compared to the tropics or the subtropics. The frigid, cold surface of the Arctic Ocean, for example, maintains its stability, and the air is dry. Now, in the second example, when the air mass moves south to cover something like the Great Lakes, it brings drought and bitterly cold temperatures along with it. Vegetation is killed or its growth is abbreviated, and there are long periods of below zero temperatures. What am I describing? In a sense, I'm describing the seasons, or at least how we experience seasonal change. What these air masses do and what their source region is becomes very important for our understanding of how these air masses and their interaction will occur over time. As I said before, these interactions will create fronts, in this case storm fronts. So let's take a closer look at those. Generally, winds move from east to west across the United States and Canada. This causes air masses and the air currents within them to move from areas of high elevation and atmospheric pressure down to areas of low pressure, and this occurs annually. Cold fronts develop when cold air mass moves upon a warm air mass, and it pushes the warm air upward. The cold air, being denser and heavier than the warm air, displaces air, forcing it to rise. There are characteristic cloud formations that will occur. And we'll see a very steep slope in terms of how the warm air will be rising. If the warm air mass is unstable and has a high moisture content to it, we will start to see the resulting heavy precipitation that the convection air currents develop. Cold fronts are often associated with strong weather disturbances, including sharp changes in temperature, air pressure, and wind. Another kind of front that we see developing when we have this interaction between tropical and Arctic air environments on an annual cycle are warm fronts. A warm front is where we have warm air or warm air mass being the aggressor, invading a region held traditionally by a cold air mass over a long period of time. So warm fronts generally will create a lot of the very interesting weather that we associate with spring in the Great Lakes region. The warm air slowly pushes the cold air back, rising over the colder air, the denser air mass, which again stays in contact with the Earth's surface. Here, the warm air rises more gradually than what we have with our cold front environment. We see less violent weather systems, and the associated changes are less abrupt, yet we will still get this significant rainfall. Please note that beyond the precipitation and beyond the experience of a change in air temperature, there are other factors that we can see with our naked eye that tell us if we are dealing with a warm front or a cold front at particular times of year, given where we live. And in this case, I'm using that kind of middle of the continental United States as an example for our discussion initially of storms. The other factor that we have that we can use or see with our naked eye has to do with our cloud systems. Nimbostratus to alto and cirrostratus cloud formations generally will be associated with a warm front pattern. On the tail end of this, sometimes you see some cirrus as well. Whereas a cold front pattern will give us a cirrus anvil top with a vertical cumulonimbus group below. It gives us this very extreme, almost cloud wall expression that we will generally associate with a cold front pattern and the convection air currents, which are rapidly developing as it is interacting with that warmer air. Often it is the case that along with this, the differentiation between a warm front and a cold front will be experienced in terms of the severity of storms. So storms associated with a cold front environment will be much more severe than what we see with our warm front pattern. Yet, the amount of rainfall sometimes can be greater with a warm front pattern. Please look at these developing front concepts as you start to get a better understanding of how storms form and how they relate to these more stable air masses. Compare the material that we've covered in this lecture to your readings. Sit back and try to digest it intellectually so that in our next look at storms, we'll start to maybe consider the types of storm bodies that develop. We have an understanding of how they're developing and why they're developing, but I'd like to talk a little bit more now, and this will go into our next lecture, as to the kinds of storms that will develop in these very dynamic areas of the troposphere.